As we get into these discussions about orbitals, I think it's important to understand how we represent orbitals. And before we talk about orbitals specifically, I want to talk a little bit about sound. Sound is something that I think from physics we recognize that sound travels in waves, and because sound travels in waves, we can create mathematical expressions, and we can write math functions that describe this wave nature of sound. And to demonstrate this, there's this great website by a faculty member at Penn State where he has a number of tools that show how sound waves travel, and as they interact with each other, they combine mathematically. You can get constructive interactions and destructive interactions, and these are really, as we scroll down, different interactions of waves. And so this is just a mathematical relationship, and it's shown here toward the top of the screen, this relationship. So just as sound has a wave nature, we can also talk about orbitals. And orbitals also have a wave nature. Now, this is, I would say it's less the orbital, and it's more about what we put into the orbital. So what do we put into orbitals? We put electrons in there. And electrons have definitely this wave-particle duality. And we won't emphasize the particle nature so much, but we'll really think about these wave properties. And so if we're comfortable thinking of sound as waves, and those waves of sound can mix to enhance a signal or destructively interact to destroy a signal, then we can also think of the same thing about the waves that we encounter with electrons. So it's really this. To understand orbitals, we need to consider that these things are waves. They can be described mathematically, and that's an important thing, and that we can describe electrons' behaviors by simply combining mathematical equations to see how the electrons will behave, much in the exact same way that we talk about how sound waves can interact.